I wouldn't want to miss today's lecture either. I wouldn't miss any of them. I have dreams where I am at college again and I forgot I had a class, and I like go like a month later and it's in math and I don't know what they're doing. So my advice to anybody, any class you're like, oh, I don't understand that, well, just keep going. Don't stop going. So we're setting the stage today for how you're going to work problems, round problems, basically, in this class. And I'm going to tell you that it's not just Mrs. Snipes said this is how you round it. This is like, I'll try to explain why we round, how we round. So it actually has to do with this idea that all numbers have uncertainty associated with them. All numbers except for these numbers. Okay, uncertainty means the wiggle, kind of the tolerance, plus or minus, usually 1 in the last digit of whatever the rightmost digit is. Exact numbers, they bring no uncertainty to your calculations. Exact numbers are either by counting, like counting people in this room, or by definition. Like within the English system, we have a lot of definition, like 1 foot is exactly equal to 12 inches. There's no uncertainty there. So we need to kind of be able to count what's called significant figures. Significant figures or significant digits are the same thing. Sometimes I'll call them sig figs. First off, if you're looking at a measured quantity with uncertainty, you're going to see me put little check marks next to every digit that is significant. So if it's not a 0 digit, then it's significant. So I'm going to try to go back and forth. See if I can be clever enough to do this. So the next 3 slides, if you go forward a few slides, it kind of looks like this. So if we call that the first rule, this is an example of the first rule. Oops. Okay, that's an example of the first rule. They're non-zero digits. So if I were to go ahead and put a check next to each significant figure, it would look like this. Check, 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 check. So I'd say there are 4 sig figs there, okay? The second rule looks like this. It's the zeros that get us when we're trying to count sig figs in a number. So this says that if you have an embedded 0 between 2 non-zero digits, then it's significant. And here's an example of this on this next page. So for instance, I would count the 1, and the 3 because they're non-zero. And do you see where I will count these 2 zeros? I count those zeros. So it gives us what? 5 sig figs. The third rule of counting sig figs also has to do with zeros. They're called trailing zeros after the decimal place. So think of trailing zeros after decimal place. Think of a number with a decimal, and then think of zeros after them, but they're called trailing zeros. I'll show you what those look like. Here's an example of those. Okay, so according to the first rule, I'm going to count 2 and 5. Okay, but now according to this rule, I'm going to count. This is a trailing 0 after the decimal. That one counts 2. Think of it like this. Somebody, I think of it a few ways. One is somebody really cared enough to put 2.50. Okay, that means what? Plus or minus 0.01, right? If they just put 2.5, that would have been plus or minus 0.1. 0.01, 0.1. I know it's kind of like, I'll work on that. I think it got beat up too much in my bag. So 3 sig figs for that one. Okay. This kind of talks you through, I think, why trailing zeros after a decimal are significant. So for instance, if somebody said I have 2.5, I have 2.50, I have 2.500. Of course, this first one, we have how many sig figs here? 2, very good. How many sig figs here? We have 3, perfect. How many sig figs here? We have 4 sig figs, yep, you got it. So in each of those, if you kind of look at kind of the tolerance, if we think of as plus or minus 1 in the last digit, we kind of are looking at this sort of thing. Which, if this is pounds, which scale costs the most? Probably that farthest scale, getting down to the nitty-gritty, okay? So we can take this number and we can come up with something that's called relative uncertainty. Relative uncertainty, we have 1 in 25 parts for the first one, 1 in 250 parts for the second one, 1 in 2,500 parts for the last one. Okay. So this actually has a lot less uncertainty, obviously, than this one. So in science, forget chemistry, just science in general, whether you go into engineering or whatever you end up doing, biology, numbers count. This is a lot different number than the first one is a lot different number than the last one. You might be like, well, they're the same, but no, they're not, if you write them down like that. That's what I mean by when you write a number correctly, you are relaying more information than just that number. So let's see, back to this guy. Okay, so we have another rule, and it's about the zeros. This is a different type of zero. This is a leading zero. And sometimes I call these leading zeros kind of like placeholders, and you'll see what I mean. They look like this. Sorry, my thing got kind of messed up, but hopefully you can read this. Oops. Oh, that's not a leading zero. Actually, these zeros right here, these would be trailing zeros after the decimal. So I'm like in 1, 2, 3, 4, 5. Those are significant. There's 5 sig figs there. This next one must be an example of leading zero. This is an example of leading zeros. You see what I mean by placeholders? Okay. So 0.00023. Now we need these 3 zeros there because they kind of give the power of 10 of our 2, 3. But they're just placeholders. So I kind of try to show you why they are not significant. I'm going to put an X over those. In your problems, if you go ahead and do the check marks and the X's, feel free to do that because sometimes I'll do that in my answer key. So for that reason, there's only 2 significant figures here. Let's see if this takes me out to that. Why are those placeholders not significant? Why are leading zeros not significant? Well, first off, they're important because sometimes students go to write their final answer. Well, they're not significant, so I'm not going to put them in my final answer. You have to put them in your final answer because it doesn't make sense to you. But if we look at it this way, where each of these values, 25, 2.5, 0.025, 0.000025, how many sig figs do those each have? 2 in all cases. Yeah. And actually, if you do the kind of chasing it around what sort of relative uncertainty you have, if you go plus or minus whatever that last digit is, in each of these cases, you're going to come up with the same 1 in 25 parts is your relative uncertainty in each case. 2 sig figs. All right. Let's see if this will take us back to. Now, here's one for you. And we'll talk more about this. I have a few more slides, so I don't want to get ahead of myself. But if somebody puts like, the number 51,200. We'll say pounds. So where is the decimal? Yep, the decimal's after the last zero. It's like one of those things where you impose, but that's not there. Sometimes what I'll do is I will go ahead and put the decimal that we all see, and I'll put a dot, 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 dot around it, meaning I put it there. Okay, that's what we call an implied decimal. Okay. And I'll just go ahead and kind of finish this thought if that's okay with you. If it's an implied decimal, go ahead and rewrite this. 51200. There's a decimal there, it's implied. Okay. If that's the case, what we do is we assume that actually they only know it out to the nearest hundredths. Okay, they didn't put a decimal there. So 3 sig figs. Let's say that they do put a decimal there. Okay, now that's not an implied decimal, that is what we call an explicit decimal. And again, I kind of go back to somebody cared enough to say, dude, that's the situation, it's explicit, and in that case, your tolerance is back to just that, the ones, okay? In that case, with an explicit decimal, we're back to 5 sig figs. Okay. This is called an implied decimal, and it's actually kind of ambiguous. You might have some problems to hand in to say, well, how many sig figs do we have? Well, if it's an implied decimal, there's a bit of ambiguity. What a cool word that is. It's ambiguous, okay?
All right, we did all of these. Did that one. Sorry about this. Did that one. Okay.
So instead of 51,200, what if we take the number 32,000? We know there are at least 2 significant figures because there's 2 non-zero digits. But we don't know if it's plus or minus 1,000, plus or minus 100, plus or minus 10, or plus or minus 1. Kind of where the uncertainty lies. This kind of says what I said. It's becoming somewhat accepted that if the decimal place is shown, now that would be explicit, if it's shown, okay, then all zeros are significant. If it's not shown, then we're conservative and we go with just the non-zero digits. Unless they're like the zero between 2 non-zeros, then they count. Okay, that's how that works. So for instance, in this example, that is an explicit decimal, so that we go ahead and give that the 5 sig figs. Now you might be like, well, what if I have 4 significant figures here? What do I do? Well, there's a way around that, okay? And your best way around that is to take this number, 51,200, and to pack it up in scientific notation. So I added this today in my office. In the corner, I said, you count sig figs in the coefficient if you're dealing with numbers that are scientific notation. So I'm assuming we're all, and if you want help with scientific notation, let me know. But you'll definitely use scientific notation in this class. I think OpenStax might have some help in the appendix. But with a number that's packed up in scientific notation, like that one over there, we could pack up 51200. Implied decimal there. 1, 2, 3. 1, 2, 3, 4. Yep, I'm liking 4. So I go 5.12 times 10 to the 4th. Okay, that's the number packed up in scientific notation. Now in scientific notation, we count. Oh yeah, sorry. So this right here is called the coefficient. It's funny because, as some of you guys know, in chemistry we have another thing called the coefficient that I'm sure there's a link between these two. But anyway, I'm trying to let that go down.
That works.
So that's the coefficient, and I think they call this the exponent. Until I'm not a math teacher. Okay, so count sig figs in the coefficient. So, for instance, back to that 32,000. If you take 32,000, back up scientific notation, you move the decimal place over from the right back to the left, and you'll have to move it 4 places, and you'll get a number 3.2. But let's just say that you wanted to show, instead of 2 sig figs, show 3 sig figs. Well, you could do that, and this is what it would look like. So in the coefficient, you would put a trailing 0 after the decimal. And if you wanted to show 4 sig figs, 3.200 times 10 to the 4th. And my favorite, 3.2000 times 10 to the 4th. But you're like, why would you do that when you could, as I've been saying, you could do this? That would be 5 sig figs too. So sometimes, I guess it's kind of being creative. Sometimes you get to the end of a problem, and you're like, oh, I know I need 3 sig figs. How am I going to do that? So just keep this in mind. This is the conservative thing I mentioned. This kind of goes back to here. If it's ambiguous, you have to go with the fewest number of sig figs. 1, 2, 3. Okay, so we talked about uncertainty. We talked about counting sig figs in measured quantities. Now, how are we going to kind of bring that together? Once you do your calculation, how are you going to round your answer? Well, it depends. There's a big old break between whether in calculating your answer, whether you were adding and subtracting, or whether you were multiplying and dividing. I'll kind of try to show you why this is. Honestly, sometimes you're doing both. So you get to kind of figure that through if you're doing both. In chemistry, we do a lot more multiplying and dividing than we do adding and subtracting. But let's just say that you've measured 2 volumes and you want to add those, you want to sum those 2 volumes. So notice that these must have been 2 different pieces of glassware, because man, we definitely know a lot more to a higher precision with the first one than we do the second one. Now remember what I said Monday, was that all measured quantities like this have uncertainty, and uncertainty is in the rightmost digit. So here you see those numbers. We're going to line them up on the decimal, and we're going to add them together. The red hot is the uncertain digit. In our final answer, we are only allowed 1 uncertain digit. So you're going to kind of see how that, what we say, propagates through this little addition problem. So there's the first quantity, okay? And here's the second quantity, 26.4. Where's the uncertainty? In the 4. Okay, these zeros are just to kind of show you so I can have this all make sense. So you line them up and you add them up like you're used to doing. So notice anything that's red is uncertain. So we got red here, uncertain, red here, uncertain, red here, uncertain. It's like a contamination sort of thing. So we can only keep one uncertain digit, so we got to truncate this right here. We can only keep that number in the 10th place. And I'm hoping we're all on the same page with this. So since this is a 4, beyond the 6, do we leave it a 6 or do we round it to 7? So leave it a 6. Yeah, exactly. So our answer is 29.6 milliliters. Bottom line, though, is you just go with the fewest decimals. I think that first slide I showed you a minute ago. If you're adding and subtracting, it's fewest decimals. In this case, I had 2 terms. Sometimes on my answer key early on, you'll see I count decimals. I count decimals for this one. I got 1, 2, 3. I have 3 decimals. It's not sig figs now, it's decimals because we're adding. And I have 1 decimal here, and it's always fewest, so 1 wins out. And notice we have 1 decimal here. Okay, I just kind of showed you how it propagates through. You're not going to kind of do the whole red number and all that. Okay? Okay. So adding and subtracting, it's conservative, fewest decimals as the terms you're adding and subtracting. Multiplying and dividing, you look at everything you're multiplying and dividing together. It might be 2, 3, 4, 5 terms. And the fewest number of sig figs is what you're allowed in your final answer. So sig figs. So for instance, let's just say that we want to knock out the area of a rectangle. Of course, area is length times width. So in this case, what you're going to see here in a minute, so area, length times width. So area in this case is going to be those numbers multiplied by each other. So we show multiplying by each other just by putting them in parentheses. So 12.34 centimeters, goodness gracious, times 1.1 centimeter. So that's what it's going to look like. Now I would count sig figs. So how many sig figs do we have in 12.34? Oh, I know. Hold up your hands, please. How many fingers? Oh, I've got it. 4 sig figs. So I would put a 4 here. Okay. How many sig figs? Use your fingers in 1.1. I'm liking 2. Yep. Put a 2 here. So without all the to-do that I'm going to show you, you know that you're allowed 2 sig figs in your answer. Bottom line, throw in your calculator 2 sig figs. But I want to show you what that looks like. We've kind of considered that certainly as it properties through. So old-timey multiplying numbers together. I mean, it's been so long, the long multiplication. But I'm pretty sure, don't you take this number, and I'm going to multiply this number here in the bottom. It's red hot. You know why it's red hot? Because it's the rightmost digit in 1.1. I'm going to multiply it up here. Now when I do that, it kind of contaminates all those digits. Okay? So I get a red hot 1, 2, 3, 4. That was this number times these. And then you slide it over one, right? And then you take this number times these numbers. The only number that's going to be red hot is the 4. Okay? So it looks kind of, I know it's like, looks kind of cross-eyed, but these are my columns. Okay? And then you say, I have 3 decimal places, that's where I put my decimal number. Okay? So bringing these down, notice that we have 1, 3, 5, 7, 4. Just writing out. And sometimes students will say, so Mrs. Snipes, you're a stickler for making me show all my work. Do I need to show all this work? No, not this work. Okay. But anything you put in a calculator in general, you should write it down. So anyway, can you see where we can only leave one uncertain digit? So we got to stop. We've got to truncate it between the 3 and the 5. We can only keep our uncertainty begins in the 1's place. So now, how many people think I'm going to leave the 3 the way it is? How many people think I'm going to round it up? Totally going to round it up. That's it. But do you see, you guys told me I have 2 sig figs here with this term, and you guys told me I had 4 here. Do you see where actually when we do that, we are going with 2 sig figs? Okay? I mean, anyway, it's kind of fun. 2 sig figs. So you round according to sig figs if you're multiplying or dividing, round according to decimals, or tens places if you're adding or subtracting. There you go. That's the summary. And I'm going to hold you accountable. Yeah, we're not going to go yet, but I'm going to hold you accountable for this in everything you do. So don't forget, though, if in your some chemistry calculations are this big, some chemistry calculations are this big, you know. So if anywhere in there you start to kind of assess how you can round your answer, if it's an exact number by counting or by definition, you don't limit your round, you don't round your number according to that. Okay, you round according to the ones that have uncertainty with them. So dun dun dun. This will be due on Friday. We're going to go ahead and start the next part. We won't get all the way through it, but starting the next part is going to help us out in tomorrow's lab. Definitely. it was kind of fun grading your stuff because I think it's going to be kind of fun because all I got to do is open a Canvas and click on my own link to my answer key. So anyway, I think it's all going to work out well. Again, I wouldn't, and you guys know this, I wouldn't go right to the answer key, but sometimes you're just like, how in the heck did you do that? You know, it's 1 o'clock in the morning and I got to know. So you can know. What does it do Friday? Maybe. All right. Cool. Yeah, tomorrow's lab. Let's see. Remember, you guys are, for sure, you guys should bring your goggles and all that. But for sure, you need to bring your notebooks, like your composition notebooks, because you're going to take your data and then you're going to write it up. Okay, so that's tomorrow. So, yes?
Do we write our pre-labs in the composition notebook?
That's a good question. No, just in your pre-labs, just go ahead and take your lab manual, go to the back section and just write in there.
Oh.
Yeah, that's a real good question. And then what I'll do kind of early on in the lab period is once I get you started, I do pre-lab, then I'll kind of make the rounds and kind of look at your pre-lab you filled in. Yeah. No. So we're going to miss Miss Sierra tomorrow. She's got a conflict, so Trent. Tomorrow we'll be looking more at density. Density is kind of how squished something is, high density, or how fluffy it is, low density, right? The air is low density. The earth is high density. A few things about density that I've seen throw students off is some textbooks, and I think biology is really notorious for this, they will use the symbol capital D for density. And here in physical science, we actually use the Greek letter rho, which looks like a P. So that's actually a rho. So that is a symbol for density. And density, we're going to be doing some calculations here in class. Okay, but density, all you got to do is take an object somehow, okay, confine your object. You get the mass of the object, and you get the volume of the object, and you divide them. Okay, so you isolate what you're interested in, get its mass, somehow get its volume, and you do a little division. In chemistry is not like physics, in that in physics we do a lot of equations like this, and you kind of plug in. Chemistry is more, and I'm going to show you this process called factor label, but chemistry is not plugging and chugging. The most time we'll really kind of use an equation in chemistry will be the ideal gas law equation when we get to gases in Unit 5. Okay. So how fluffy something is or how compact it is actually depends upon the temperature. I'll just put all these up here. Most substances, I'm going to set my water aside here because water is anomalous. But most substances, like if I take the steel, stainless steel, most substances, as we cool them down, all substances as you cool them down, the little molecules go slower and slower, so they actually, as a set, occupy less volume. So it's becoming kind of squished, it's becoming more dense things as they cool them down. Now, solids do that to a little bit. Liquids do that to a more extent as you cool them down. And gases, oh my gosh, if you have a gas at a certain temperature and you cool down that gas at the same, assuming it's the same pressure, the volume will definitely reduce a lot. So it's definitely, density is a function of temperature. This is clever. So all this is this is all water. Of course, you recognize the ice cube, that's water, but that's cold water, right? That's water in its solid state. Notice that since it's floating, things float if they're less dense or more dense. What do you think? Less dense, right? Exactly. It's floating because it's less dense. Good for us because I think I told you the other day, yeah, if all the, yeah. So ice will float, but notice that Why is this blue sinking? That blue water sinking? What do you think? You guys told me ice floats because it's less dense. What if something sinks? It's more dense, yeah. So all somebody's done is to kind of say, hey, if you have some kind of dye floating up here, and in the vicinity of the dye, you cool that water down, then that water that's containing the dye, as it cools down, will get more and more dense. Okay. And actually water, as you cool water down, its density does increase. I'm going to show you a graph here in a minute, but it does this crazy transformation just on the other side of 4 degrees Celsius on its way to freezing, and it rearranges and it fluffs out. So that's why ice floats. And water is different like that. So density, or the volume that something occupies, is very temperature independent, or temperature dependent, excuse me. So you recognize this is a volumetric flask, and this is a pipette. You guys have been using these. The pipette I showed you the other day has like one ball in it, or one bowl kind of thing, and have one calibration mark on it. This is actually a pipette that has multiple calibration marks on it. Okay. But they have the TD, which means, what's TD mean? Remember, it's kind of like why you don't. Like, take your pipette, blow it out. TD means two.
I know.
Like, it means how much it's supposed to deliver. So, yeah, to deliver. To expend. But it's calibrated at a particular temperature, 20 degrees Celsius, 20 degrees Celsius. Which I'd have to, I could Google it, like convert 20 degrees Celsius to Fahrenheit. But I'm thinking that might be around 80, mid-70s. Okay. So in the first part, we talked about this idea of properties. And when it comes to density, actually density is a physical property. That makes sense. Okay, you don't have to do any sort of chemical reaction to get the volume and the mass of something. The other thing is it's independent. It's independent of amount, so it's an intensive property. So this is to say whether independent of amount, this is to say whether I was talking about the density of a cup of water or the density of a bathtub full of water. As long as they're the same temperature, they got the same ratio of mass to volume. In physical science, not just chemistry, but in physical science, the units are very important to whatever thing you're talking about. So since to get density, we're going to take mass divided by volume, it shouldn't be so surprising that our units of density will be mass per volume. Mass grams per volume, milliliters. Now this is kind of what I call the linear version, G/ml. That's great. And actually when you guys are writing up your semi-formal lab reports, that's what I would use. But this over here is kind of what I call the unpacked version. Anytime you see something per something, that really means grams, or in this case, over divided by milliliters. This right here is the way I'm going to need to see it when you work your problems. And we'll kind of see more on that. What's the relationship between milliliters and centimeters cubed? Remember? Okay. Yep, they're equal. Yep. Down here, a little less. I don't use it a whole lot, but I guess I do sometimes. If you see something, in this case milliliters, raised to a negative power, that means it's the same thing as being in the denominator. Okay. So in this case, centimeters cubed in the denominator. All right, so densities. It's a physical property. It's an intensive property. It's independent of amount. So here's a figure from your textbook. Remember, every time you see this kind of rainbow outline, that means it came from OpenStax. So solids we would expect to be, what do you think? How many people think solids should be compact or solids should be high density or low density? You don't know? What do you think?
High density.
Yeah, I think the densities should be generally high. And what your author did was just take an assortment of things pretty high density. This means for for instance, for gold, if I have a volume of 1 centimeter cubed, it's going to, or 1 milliliter, it's going to weigh 19.3 grams. So that's how you kind of look at that. It's high density. This is kind of a random assortment of liquids. This is stuff in its liquid state. This is one of my favorite things. Look, like water, the density of water, and I have a slide coming up that you're going to have to memorize the density of water, but it's 1. Density of water, 1. What would the units be? Grams per milliliter. Have fun. How did that happen? Anyway, a little bit lower density, and so we should have even lower density up here. Well, the numbers look kind of a little different, but they don't look as low as I would expect them. What's the difference between the units of this last column versus the first 2 columns? It's per liter, yeah. So instead of per milliliter per cubic centimeter, they're talking about per liter, which is what, about a quart. Yeah. Okay. So the mass per 1 liter, and a lot of times in gases, the density is so low. Well, hey, let's go ahead and I just thought of this. So dry air, 1.20 grams per 1 liter of air. Okay. So how much would it be per 1 milliliter? I think times 1,000. So by times 1,000, I move decimal place over. So like that. Wait, no, that's not right. The other way. Not times 1,000, divided. What we just did though is oftentimes, in order to kind of keep yourself on track, when I put that big number up there, that didn't make sense, did it? So how about this? We decimal place over 3 places. Yeah. I like it. Let me show you, just because I didn't totally butch it, but it's good to just, this makes sense, and it does. One of the things we're going to be doing maybe Friday is you guys would say, what's the, in 1 liter, how many milliliters are there? Yep, 1,000. So we can actually use this as what's called a conversion factor. So if I want to go from grams per liter to grams per milliliter, I can do that. 1.20 grams, 20 grams over 1 liter. And then I can go 1 liter is 1,000 milliliters. And our units cancel, we'll have the units of grams per milliliter. And if you divide the 1.20 times by 1,000, you get the 0.0012 grams. So anyway, I just thought that was interesting. When I think about this sort of thing, a few slides ago I said, what are units of density? Well, they're grams per milliliter, grams per cubic centimeter. No, it's again, probably grams per liter. All right. So let's kind of see what this looks like. And you're going to be doing this in lab tomorrow. You're going to, for a couple of objects, you're going to get the mass, and for a couple of objects, you're going to get the volume, and then you're going to go ahead and divide and get the density. Okay? So in this case, we've got a metal alloy. It happens to be nice, sharp sides. It's a block. So how can we get the volume? How can we get the volume if we're given the length, the width, and the height? Well, exactly. And that's the sort of thing that, and so then the mass was given, so all we got to do is divide that volume by that mass. And a follow-up question is, if we were given a table of the physical properties of metal alloys, then we could match up density we came up with what the literature says. Length times width times height. So there's the 3 dimensions. Now this is where I said you need to write everything down. So if you put it in your calculator, or even if you can do this in your head, even if you're a brain man, okay, you should be writing it down. Pull up my calculator here. So on that volume, how would I round? Use your fingers again. How many sig figs would I likely for the volume? Fingers? 2. I'm seeing lots of 2. Yep, only 2. So 1 times 1.05 times. Okay. So you guys told me 2 sig figs. I get 1.76358. So 2 sig figs from left to right. I'm gonna write it down. This is a good example of when do we round. I'll kind of show you how this works. You might be, well, do I need to round it there, or in a minute, I'm gonna go ahead and use that volume and take the mass divided by the volume to get the real answer what I'm after. So I'm gonna write that down. B is equal to 1.76358. What would the units be? Centimeters cubed, exactly. Centimeters times centimeters times centimeters, which is centimeters raised to the 3rd power. Perfect. You guys told me 2 sig figs, so how do I need to round that then? Yep, 1.8 centimeters cubed. Perfect. You got it. Communication. And they gave you the mass, so now we're ready to knock this out of the park. So to calculate the volume is one last division. We're going to take the mass they gave, 13.94 grams. Is there uncertainty in that number? 13.94 grams. That's right. She says there is uncertainty, and it begins right here in the 4th place, or the hundredths place, the digit 4. Yep. So there's uncertainty there, uncertainty 1.8. So show me figures. How many sig figs we need to get. Yep. Oh, very good. So when I divide that out, you guys told me 2. I get density is equal to 7.74 repeating. What would the units be? Yep. Guys got it. Gram per centimeter cubed. You guys told me 2, so I'm going to go from left to right. I'm going to keep this digit, I'm going to truncate it. So what would it be then? Yep, 7.7 grams per centimeter cubed. Well, I'm here to tell you that this would be, oh, and one thing I forgot to tell you, if I grade anything, if I go like that into your assignment, that means you got it totally right, okay? Sometimes I forget to tell people that. If I go like that, that means it's wrong. I know. Check just means I looked at it and it's wonderful. See, smiles all the way around. And then this would be rounding these. And then if I do a line, I'm kind of like, I'm not sure what to make of that. Okay, so now the reason this is different is because I used the unrounded value. I used this in that last calculation. You know how calculators are smart, you can kind of store a number or whatever. Either number's great, but if I go ahead and I take 13.94 grams divided by 1.76358 centimeters cubed, okay, you're going to get a number rounded to 2 sig figs, which is 7.9 grams per centimeter cubed. The difference is I use the unrounded value. Sometimes students are like, well, isn't it better to use the unrounded value? Usually it's not, the difference isn't this drastic. An advantage of using the rounded value, an advantage of doing this and getting 7.7, I really like it, is because it clearly shows you how you need to round your final answer. Using the unrounded value, not so much, that 1.7 is. Okay, and I said it's all about. Well, that's a good place to stop. And so Friday, we'll kind of finish up talking a little bit about density, go to mass percent. Maybe between the next part, we'll see. So see, I had you for introduction, and we talked about this. We'll miss you. Hey, good luck with it.
I'm getting there eventually.